Okay, we've been learning about the standard distribution, and let's just recall what we've already learned. We've learned that the standard distribution is anything that takes this form. So we've got mu is our mean, and this is our standard deviation. And we found out that if we take our standard deviation and we have it in the standard normal form, so the mean is now centred upon 0, and in the standard normal form we've got a variable z, and it has a 0 mean and a standard deviation of 1, we can use the tables to find out the probability. Now, it's obvious that in real life examples you're not going to see this very often. You're going to have a huge range of different means and different standard deviations, and we can take any form of any standard distribution and we can put it into the standard normal form, and we do that by coding the data. So let's say we have a variable x, and say we want to, if we subtract mu from x, then the probability density function is translated horizontally by minus mu. So what would that look like? So say we had our, here's mu, and here's our standard, our normal distribution, and now we're taking our variable x and we're minusing mu. So now what we've done is we've shifted it so the mean of the new mean is now at 0, but it's still got standard deviation sigma. So if we now take x minus mu and multiply by 1 over sigma, then we are going to then change it so that, I'll change the colour again. So now the sigma is 1. So now, oops, change the colour back to black. The coded variable x minus mu over sigma is now normally distributed with mean equal to 0 and variance equal to 1. So let's write this out. Let's get rid of the colours, and so what we have is when x is some normal distribution with mean mu and variance sigma squared, then x, when x equals when z equals x minus mu over sigma, it has been a standard normal distribution. Oops. and a standardized value of little x equals little z, sorry, equals x minus mu over sigma. Tells us how many standard deviations I was going to say standard SD for standard deviations x is from the mean. And what this means then, we can now use our normal distribution tables to find a probability of any normal distribution. So, for example, say we had x is normal distribution of mean 29 and variance 9, then the probability that x is less than 23, so if we think about, here's our normal distribution, and here is our mean of 29, here is our 23 here, and so we're looking at this this probability. That's going to be the same as the probability for z less than, we take this and we code it, so our x is 23, our mean is, oh wait, I've wrote the wrong number there, sorry, mean is 20, let me just change that, so mean 20, that's 23, so here, sorry, that's the probability we're looking at. So 23 minus 20 over, now it's sigma, not sigma squared, so it's the square root of 9, which was obviously 3. And there we can take the value we get for this and plug it into, or look up our tables for that value. So let's do some examples of how this is going to work. So we're given that x is a normal distribution with mean 11, variance 25, and we want to find the probability that x is less than 18. So z is going to be our little x minus mu over the standard deviation. So that's going to be 18 minus 11 over the root of 25. And if we do that, we get 1.4. So the probability of x less than 18 is the same as the probability that z is less than 1.4. And so we're going to look that up. So that's our phi function for 1.4, and that gives us, if you look up the table the way that we were doing in the previous lesson, you'll find it's 0.919. I'm not going to look up the tables in this lesson, just for quickness. So given that x is the normal distribution where the mean is 20, 7 is the variance, find the probability of x less than or equal to 16.6. And we do it always to 3 significant figures. So let's find out what our new variable, our coded variable z will be. So we take our x, which is 16.6, minus 20 over the root of 7, and that's going to give us minus 1.285. So let's look at this. Let's draw our coded variable, z. So this is going to be minus 1.285 here. And we want the probability that for x less than or equal to 16.6, and we've found that that's going to be the same as the probability that z is less than or equal to minus 1.285. So it's going to be this value here. Now we know from our last lesson that that is the same as saying 1 minus phi function for the value of positive 1.287, which will give us 0.0994. Now, we're given that x is a variable that's described by normal distribution, mean 5, variance 5. And we want to find the probability between the values of 2, x between 2 and 9. So let's just draw this here. This is not the y-axis, because this is the value of 5. This is where the mean is. This is our mean. And we want it between 2 and 9. I'm just going to do this in a different colour. So this probability. So we need to code for each of these variables. So we've got for x equal to, z is going to be 2 minus 5 over the root of 5, which is minus 1.342, which we would expect because it's on the left hand side of the mean. So when we draw it around 0, this is going to be minus 1.342. And for x equals 9, z is going to be 9 minus 5 over the root of 5, which is 1.789. So this is over here, 1.789. Here is our what we're interested in. So for this one, we'll find the area for the right hand side. So we're going to find this area first. To put a different colour. So we're going to find this area first. So that area is going to be the phi function for 1.7889, not 9889. So that would be this whole area here. But we're going to take away this. So I'm just going to draw for that one part of it so it makes sense. So we've got 1.789. If we do that, that is going to be this whole area. But we are going to take away the probability of this. So we're just left with this part here. So it's minus phi of 0, which is going to be, whatever the value is for 1.789, so you'd have to go and look that up at the table, and actually obviously the phi of 0 is half, because obviously that's symmetrical, the area is 1, and so you're chopping off half of it. 0.4633. Now, we want to deal with this area here. So we're going to take, this time, the phi of 0 minus the phi of minus 1.342, so that's 0.5 minus, but remember, when we've got we're dealing with a negative number, we do 1 minus the positive 1.342. And that then gives us 0.4102. The thinking behind this is exactly the same. I'll just draw it just to make it make a bit more sense. That's meant to be symmetrical. So here's our minus 1.342. So when we find this value here, which is this value here, is the same as all of this. But we only want this bit, so we take away, we've got this bit here, and we're taking away that to give us the probability that we want. Now we can, so now we wanted to add these two together to give us the total area. So the total area will be this and this. Which is 0.874, which is the probability that we want. Now, through the last two sections, we've come across lots of different there's different ways that we can just standardize a lot of these examples. So these are some useful results that is useful just to know, to save you time working out. So if you have, this is our normal distribution, so say we have a value A and a value B, and we want this probability. So we want the probability that A is less than Z is less than B, then that is just going to be the phi function for B minus the phi function for A. Now if we have two values, minus A, so this is like what we just did, and some value B which is different, and we've got this area here, so the probability of Z being between minus A and B, we do phi function for B plus the phi function for A minus 1. And final result, for completeness, if you have the scenario where you've got minus A and A, the probability of Z's between minus A and A, we just do 2 times the phi function for A minus 1, which is logical if you look at that one. Okay, these are just useful to have memorized, so you can just pull them out and it helps you not make a mess or mistake when you are breaking down these shapes, these graphs. Right. Let's look at using the inverse that we've done before, but how to do it with this new coded data. So we've got some variable y, which is a normal distribution with mu and sigma squared. Now the probability that y is less than 10 is equal to 1.75, and the probability that y is greater or less than 12 is equal to 0.1. We want to find mu and sigma. So let's think about this. This is mu. This is an uncoded mu. And now when we code it, mu is obviously going to be 0. And when 10 is the value, we've got a value of 10 here. We've got this area here, and we're going to have some value of ZA. And this value here is 0.75. Now, I'm going to redo that because it's rubbish. Again, we've got mu here, and this is if it's 0, and this is our value of 12. So this is, it tells us that for greater than 12, the value is 0.1. So for less than 12, this value here must be equal to 0.90. So this is ZB. Now, for 10, so what is, that's not what we want to think about. So we now need to find out what our value for Z would be. We get rid of that. There we go. So if ZA will be the inverse for 0.75. So this probability here is 0.75, and we want to find out what value of ZA here would give us that probability. So you go and do the back engineering on the table, and you find it 0.674. Now for ZB, we want the inverse phi function for 0.90. And we find that that's 1.282. So now we can tell that 10 minus mu over sigma must equal 0.674, which gives us 10 minus mu is equal to 0.674 sigma. And similarly, 12 minus mu sigma is going to give us 1.282. So 12 minus mu equals 1.282 sigma. Oh, no, sorry. Sigma, there we go. Looks like a 6, but it's meant to be a sigma. Right, so now we've got equation 1 and we've got equation 2. So we've got a couple of simultaneous equations that we can work out. So let us do that up here. Top tip when you're writing these out, if you're doing the exam, try and make your sigmas look like sigmas and not like sixes, just in case something goes wrong and you get mismarked, or you make a mistake when you're doing a working out, thinking you've got a 6 and it's not a 6. So 1.2826 sigma. So that's going to give us, if we sort this out, we'll get 2 equals 0.608 sigma. So sigma is going to come out at 3.29. Plugging that back into one of the first equations here, one of those two, mu will be 7.78. So I hope that helps.